So, welcome. Let's remember what we were saying last week. Okay, so we were talking about analysis of linear dynamic systems, and in that case, analysis involves calculating the output of a system to initial conditions or to external inputs applied to the system, or you may have both of these at the same time. And in all of these cases, you end up with a function of S in Laplace domain, and this function is always in the form of a rational function. Okay, so the good thing about these rational functions is they are composed of some polynomials of S, and in the form of a rational function. Okay, so if you have an nth order polynomial in the denominator, this means that this function will be not analytic at a finite number of points, and these finite number of points are the poles of this nth order polynomial. So that means you will have n points, and in each one of these points the function will be not analytic. So we call these points poles of the system. So while taking the inverse of this function, these poles become really important. Okay, so the first step is to calculate where these poles are. So you need to find the roots of an nth order polynomial. So it's not an obvious task. Okay, so if I give you a random nth order polynomial, you will not be able to find it manually. So imagine like a fifth order polynomial. Unless some poles are obvious, you will have a hard time finding the poles. So that's the disadvantage here. But don't worry, in the exam you will not need to worry about that. So if I give you a large order polynomial, I will always give you the poles. Or the most difficult part will be to find the poles of a second order polynomial, for which there is a formula, and even that formula will be supplied. But I may expect you to see some little things like, for example, if you have a polynomial like that. So if this is your denominator polynomial, so you should be able to see that there is no constant term, which means that you can take S out of the parentheses and you will be left with a second order polynomial, right? So I expect you to be able to see that. And for this second order one, you can use the formula. But for more general third or fourth order polynomials, I will give you the poles. Okay, so once you know where the poles are, we use a very powerful expansion which makes the inversion really easy, and this inversion allows us to write this so this expansion allows us to write this rational function as the summation of these simpler terms, and so each term has first order denominator unless the poles are repeated, and for this you need to calculate the residues. If you know where the poles are, calculating the residues is easy manually. So we have a formula for that. So this is the formula to calculate the residues. If you have complex poles, then here you will be dealing with some complex numbers. So the residue in general will be a complex number, and then you will have a complex pole here. So this will be a complex number right there. In which case, if you invert it directly, you will end up with some complex coefficients here plus some complex exponentials. But everything will converge down to a real number. Since we are dealing with real systems. Okay, so the complex terms will be canceling each other out. Okay, so things get a little complicated if you have repeated poles, in which case we can apply this expansion, but in the expansion you will have this time not all the terms will be first order, but you will have some higher order terms depending on the multiplicity of your pole. And in that case, still these coefficients can be calculated using the formula. The formula is a little bit more involved, as you see here. But after that, the inversion is still quite easy. Okay, so the inverse of these terms are very easy using a Laplace transform table. Okay. So I guess we didn't look at this example in class last week. So let's start from here. So we are trying to calculate the response of this system, the system with this transfer function to unit step input, right? Yeah, it says here the unit step input. Okay, so first we need to obtain the response in S domain, right? Which will be obtained by multiplying the transfer function with the input, the Laplace transform of the input. For the unit step input, the Laplace transform is 1 over S. It is this S. Okay, so this is our function, right? So this is the function that represents the output of the system, and we need to find the inverse of that. So we start with calculating the poles. The poles of this can be calculated using this formula, and it turns out that it has complex poles, -1 plus -j. So here, this example shows how you end up with real functions. So let's go over this quickly. So the expansion will have 3 terms like that. This is the pole due to the input function, the unit step function. So, and these are the 2 poles of the transfer function. So you will have one residue here, another one here, and the third one is the complex conjugate of this residue. So you see the calculations. So the residue for the K2 is calculated as seen here. So you multiply the function, the y function with this term, and then insert -1 plus j instead of s. You can follow the calculation. So you have this complex number here, and then after putting everything in, you end up with a complex number in the denominator, and you get rid of that by multiplying both the numerator and denominator with the complex conjugate of this. That way you will have a real number on the denominator. The complex number is upstairs. So the residue turns out to be -1 over 4 plus 1 over 4 times j. Okay? So the residue for the complex conjugate pole is the complex conjugate of this one. So this is what I was talking about. So here, this is the inverse, right? This is correct expression. The problem is, though, you have these imaginary numbers here. You have j here, you have j in the denominator. Well, if you are using Matlab, you can directly plot this. Even though you have some complex terms, Matlab will figure out that these terms together correspond to a real number and will give you the correct response. But in the exam, I will expect you to simplify these terms and show me the end result, which is a real number. For that, you use this Euler's theorem for these complex exponentials. First, you write them as multiplication of these 2 terms. This is the complex exponential, and for that you use this Euler's formula. And if you do all the calculations and simplifications, you will see that the end result turns out to be this function. So this is the response of the system when you apply a unit step as a forcing term. Okay. Now, since we have extra time, let me show you how you study this example using Matlab. Remember, I told you that Matlab takes the partial fraction expansion with one command. That's the residue command. This command gives you the residues and the poles, everything at once. Okay, so this is the function I want to take the inverse of. So to use the Matlab residue command, I need to give Matlab the polynomials, right? The numerator polynomial and the denominator polynomial. So let me write the denominator polynomial in open form. This should be s to the power 3 plus 2s squared plus 2s, and there's no constant term. So the upper numerator is just a constant number. So it's the 0th order polynomial, and the denominator is a 3rd order polynomial. So for Matlab, I need to write the coefficients of these polynomials in descending order, right? So I start with the highest order coefficient. Since there's just a constant term here, it is just 1. But for the denominator, I write the coefficients in descending order, starting with the highest order. The highest order is the 3rd power. The coefficient is 1. The second power is the 2nd order term. The coefficient is 2. The 3rd term is the constant term. The coefficient is 2. And I should not forget the 0 here. So there's one last term, which is the constant term, but it is 0. So I should put a 0 here. Okay. So I have a row vector of 4 numbers. That means you have a 3rd order polynomial, constant term, 1st order, 2nd order, and 3rd order. Okay, so these 2 numbers are what I input to Matlab residue command. Okay, so let me just update my code here. So the numerator polynomial is just a constant number. The denominator polynomial is 1, 2, 2, and 0. Okay, so this is how I use the residue command. I give it the numerator polynomial coefficients, the denominator polynomial coefficients, and as an output, Matlab gives me 3 things. So if you want to know what these 3 things are, you can just take a look at the help for this command by simply typing help residue. Okay, so the residues are returned in the column vector R. So the first output gives you the residues. The second output P gives the pole locations in column vector, and the direct terms in row vector K. So the last term, we usually don't need that. So that's required if you have the numerator degree greater than or equal to the degree of the denominator. So if you have something like s to the power 5 plus something divided by s to the power 3 plus something, in this case the ratio will give you s squared plus some, there will be some constant terms, right? So that is what k term gives you. But for most of the functions which we will use in this course, the numerator will have a degree less than the degree of the denominator, in which case the k will not be needed at all. Okay, so let me just stop the function here and run up to this level. So these are the residues, these are the poles, and k is not necessary for this, or is not used for this example. So these should be the same numbers as the numbers we found in this example, just to be sure. So the residue corresponding to this pole minus 1 plus j. This is the pole, and the corresponding residue is the corresponding term here, which is the first one. So as you see, it's the same number. Okay, so next, by using these residues and poles, I can write the inverse transform of that function directly, as you see here. Okay, so I'm just writing this in Matlab. The first residue times e to the power first pole times t plus all these terms, and the last residue times e to the power pole times t. So this is what you see here. Residue times the exponential term, residue times the exponential term. So this is the response. So as I said to you, the Matlab gives me the result as real terms. So even though these are complex numbers, as you saw here, the R includes these imaginary parts, and similarly the P involves imaginary parts. But I can type this directly in Matlab without worrying about these simplifications. Okay, so let me just run this and it will give me the plot. This is the last step. Okay, so this is the response we just calculated. Okay? Okay, so let's experiment on this simple code and let's try different numbers. Well, anyway, so remember these were the physical properties of the system, right? So the function. So in the general sense, this was really 1 over m s squared plus bs plus k. Okay, so let's see what happens if I change the spring constant. So the spring constant value was 2. So let's see what happens if I use that 2 is this 2 here. So if I use a stiffer spring, so that means the spring gives me more force per deflection. So let me increase this number from 2 to 5. So the response is this function here. The original response was here. So if I give a stiffer spring, the steady state deflection is less, which makes sense, right? Bir ara ara şey yapsam iyi olur ya. Sizi çoktan mı kaybettiğim, nerede kaybedeceğim onu şey yapmak için. Şimdi which makes sense dedim ya. Tabii benim aklımda şu geçiyor. So if you remember the original system, there was a mass here, there was a spring here, and a damper here, and this is where we applied the force, right? So if you apply 1 Newton of force, at steady state, this 1 Newton should be balanced by your spring here, right? So the spring should, at steady state, when the car is not moving, if this is not moving, the damper will not do anything, right? The damper gives you force when there is motion. Remember, B times x dot or y dot. So when this is not moving, this is the only thing that can give you force. So if the spring constant is 2 here, for this is newtons per meters, if you apply a 2 newtons of force, there will be 1 meter deflection. Okay, but instead, if this is 5 newtons per meter, then for 2 newtons of force, there will be less deflection, right? Şimdi hesaplamaya çalışıyorum bir saattir kafamda. 5 times x should be equal to 2, so x should be 2 over 5. 0.4. If you increase it further, then if you make it, let's say, 10, then the deflection will be even less, right? The deflection will be just 0.2. So that's why I told you it makes sense. So let me make it even stiffer. So let me increase this spring constant to 10. So this is the last one. And if you increase it further, the steady state deflection is even smaller. But not just that, the characteristics also change. So you see an increase here and then decreases and it settles down. But if you look at this response, you see that it increases, decreases, increases and decreases. There are some oscillations before it reaches the steady state. So these are the things that are important here. So anyway, let me bring this back to the original. And let me change this number, which is the damper constant. So let me increase this one, for example. Let me increase from 2 to 5. Well, it may be hard for you to see, but this was the latest response. Okay? Let me make it smaller. Let me make it 0.5. The newest response is this one. Make it even smaller, like 0.2. So it starts to oscillate more and more, as you see here. Anyway, so we will talk about all these details, don't worry about that. So we will see, talk about what makes a system oscillate like this one, or what makes a system go smoothly to some constant number without any oscillations at all. So these are all related with those pole locations. Anyway, so this next thing I'm going to talk about is important, especially in the exam. You may find this helpful. Okay, so in the exam, if you are asked to calculate the inverse of a system with some complex poles, you will need to make a simplification here, right? So you will need to make, some multiplications and summations and subtractions to do the simplifications. Another way of doing that is to keep these two terms as a second order term. Okay? That way there will be no complex numbers at all, but instead you will be required to take the inverse of a second order function. So in the next example, that's what we do. So we go back to the same example. So let me add some explanations here. And to find niye böyle gidiyor ya? To find the response in you need to make simplifications to make the results real. Instead of doing that, you can leave the complex pole pairs as second order terms in the expansion as follows. Okay, so we know that there's a complex pair of poles here. So instead of this expansion, we can write okay, so in the third case, there were two residues to be calculated. But in the second one, there's this residue, and then there's the second order term. Okay, and this, for the second order term, on the numerator, I should leave a first order polynomial. So there are now two numbers to be calculated, A and B. The bad thing here is that there's no simple formula, as far as I know, for calculating these A and B numbers. For these, there's a formula, and you can calculate residues very easily using that formula. But in this case, you need to find them manually. And for this example, you can see how it is done here. So we just calculate both sides of this equation, and then for finding A and B, so A is the coefficient of the square term, but there is no square term here. Well, no. Well, anyway, the calculation is shown here. Okay, so you collect the, you obtain the polynomial here. The S square term is A plus 1 over 2. The S term is B plus 1, and the constant term is 1. So these are your A and B values. So once you do that, this is your function. Okay, so the original function can be written in this form. Now this is what we need to take the inverse of. The inverse of this is easy, as we had that term before in the previous example. Now we need to invert this one. Okay, so to take the inverse of this, we refer to Laplace transform tables. Let me show you. So this is a Laplace transform table from a previous exam. So the similar, or the most similar thing in the table is there are two functions here. So this is similar to what we had there, and this is also somewhat similar. So we need to take what we have here and make it look like these entries. Okay, so here you have s plus something squared plus a constant number. Okay, so there's a second order polynomial here without a constant s function. Okay, so if you have a constant s term here, you need to somehow get rid of it by making this square term. So I should make it look like s plus something squared plus another something. Şimdi bunu yapmanın birden fazla yolu var tabii. So first you can open the square, which gives you s squared plus 2as plus a squared plus b. So from here, by comparing this thing with this thing, I can directly write that A should be 1, right? And A squared plus B should be 2, which gives me B is 1 as well, right? So this is equal to S plus 1 squared plus 1. And on the upper side I have S plus 2. Okay, so my A is 1 and B is 1 as well. Let me go back to my table. And if on the numerator, if I have S plus 1, since A is equal to 1, then this is my term, right? So let me then write it as like that. So if I have S plus 1 here, then S plus 1 squared plus 1, then inverse of this is already given in the table. But it's not what I have, right? I have another term here, which is, there's 1 left here. I should still keep that. So the inverse of this is e to power minus t times cosine t plus the inverse of this. And luckily that second term is this one directly. Ne oldu? Evet. Ben buna bayağı şey yapıyorum ya. Sınavı hazırlarken bu kısım hakikaten zorlayıcı bir kısım oluyor. Yani o denk gelmesi işi. Minus t times sine t. Okay, so this is another way of handling complex poles. Sınavda yani geçmiş sınavlara bakarsanız aşağı yukarı hep aynı tabloyu veriyorum. So if you look at previous exams, this is pretty much the same table I use for all the exams. But obviously that may change, so I may want you to see some detail and then change the table accordingly. But you will be, well, I will expect you to use this table though. So don't, for example, onu sorman iyi oldu. Bu da şeyden bahsedelim. Okay, so this entry is in the table directly, right? But instead of putting this entry, I can give you the Laplace transform for sine and cosine term only, and then in addition to that, I can give you the complex shifting property. So using the two, you can obtain this. So you should be looking out for such simplifications. Okay, so do you have any questions? Okay, so let's just give a break here and then continue after the break.